Bismillah ar-Rahman ar-Rahim. Now we are going to solve some problems related to standing waves, and these problems are selected from old exams that were given in the physics department at KFUPM. Before that, let me review just quickly with you resonance in a string. You see this string here has a length L, and it is at rest. Once I start sending a wave from this side, this wave will go and is reflected, and you at certain frequencies, we call them the resonant frequencies, we form standing waves where the amplitude is maximum. You can see here. You see here the length here of the string is not changing. What is changing is the wavelength. You can see the wavelength here in this figure here. The wavelength actually is 2L, and here the wavelength is L, and here the wavelength is 2L over 3. You can see as you go from one frequency to another, as the frequency here is increasing, the wavelength is decreasing, because we have V equal lambda F. And V, in this case, V is the speed of the wave here in the strings is constant. So as the frequency increases, the wavelength is decreasing, as you can see from here, okay? That's one thing. The other thing is, I want to draw your attention to this resonant frequency, Fn, which is drawn from here, F1. The resonant frequency is N, V over 2L. V is the speed of the waves, those two waves which are interfering, okay? Or making the standing waves. Of course, that standing waves actually is not moving, but the two waves are continuously moving with speed V, and L is the length of the string, as you can see, and N is the number of the resonance number, let's say, or the number of segments. Here we have one segment, here we have two segments, three segments, and every segment has a length of lambda over 2. Okay, so I have lambda over 2 here for this segment, another lambda over 2, so L will be lambda, okay? Here lambda over 2, lambda, 3 lambda over 2, and L will be lambda will be 2L over 3, and so on. So he's asking what is the frequency of the third harmonic standing wave, okay? The third harmonic, this will be the third harmonic. This is the first harmonic or fundamental mode, this is second harmonic, this is the third harmonic. So he's looking for F3. But you know that Fn, for any frequency, Fn is Nv over 2L. The next one, the next highest frequency is N plus 1 V over 2L. If I subtract them, 256 minus 224, I get 32 hertz. And that is equal, if you subtract, you get V over 2L. That's actually F1. So F1 for this problem, F1 is 32 hertz. And he's looking for what? Which frequency he's looking for? He's looking for the third harmonic, which is N equal 3. So he's looking for F3, which is equal to 3 F1, as we know. So this will be 96 hertz. And that's the answer for this question. The next question I want to look at, let me erase this example number 1. We go to example number 2 now, and let me erase this. Okay, example number 2 is the following. Example number 2 is the following here. Okay, number 2 is I have two sinusoidal wave having wavelength of 5 meter and amplitude 10 centimeter, okay? That's the amplitude of these waves, okay? And traveling in opposite direction. You can see here, when we say traveling in opposite direction, means they're going to give standing waves, but at certain frequencies, of course, not all the time, okay? At certain frequencies of your source, they produce standing waves. On a 20 meter long stretched string, so my string has a length of 20 meter, that's the length of my string, okay? And excluding the nodes at the end of the string, how many nodes appear in the resulting standing waves, okay? How many nodes? It means that if we see here, for example, in this figure I have only one node. In this figure here, which was before here, I had 2 nodes, you see? So he's asking about how many nodes, excluding the ends, okay? If I exclude the ends, here I have no nodes. Here I have only one node. I exclude the ends, okay? So he wants to exclude the ends, okay? The 2 ends here. So he's looking for the number of nodes for this special case here, okay? So the wavelength is 5 meters. So if I divide the length by lambda, and I know lambda give me one node, okay? So if I divide the length, which is 20 meters, by 5, which is 5 meters, okay, I get 4, okay? 4. So I have 4 wavelengths, 4 shapes like this, okay? But because this is one wavelength. So let me draw them here. And so I have one of them will be this. This is one. And the second one is this. The third one is this. And the fourth one is this, okay? So let me complete my standing waves picture and see how many nodes. Now I'm going to exclude this one, and tell me, my son, how many nodes I have in this figure here. So, by the way, I did not use the amplitude. The amplitude given in the problem, I have not used it. I use only the length of the string and the wavelength. And the wavelength, this is one wavelength, okay? So this is 5 meters, another 5 meters at 10, and this is 15, and this is 20. And that's the length of the rope. Let's count how many nodes I have. This is one of them. He said excluding these two. 1, 2, 3, 4, 5, 6, and 7. So there are 7 nodes. Okay, let me write down here. 7 nodes in this special case. Excluding the 2 nodes at the end. That's what he wants. Okay? And how many antinodes I have? The number of antinodes will be the number of nodes plus 1, always like this, okay? Let's count them. I have 1 here, 2, okay, 3, 4, 5, 6, 7, and 8, okay? So there are 8 antinodes. If he asks about the number of antinodes, okay? He did not ask it, but he antinodes. If he asks, that's how you find it. Now tell me, which frequency is this? Which resonant frequency is this? This is F1, this will be F2, F3, F4, F5, F6, F7, F8. So this is F8, okay? This is the 8th harmonic, okay? F8. This figure here corresponds to F8, okay? So this is, because I told you N, the N here is the number of segments you have, okay? If it is F1, you will have only one segment. If it's F2, you have 2 segments. F3, 3 segments, and so on, okay? So I have 8 segments here, means that's the frequency, the 8th resonant frequency, which is 8V over 2L. Now, if I was given the velocity, the speed of the wave, the waves, I can find this frequency because the L is given to you 20 meters, okay? The next problem is example 3. Let's look at example 3 now. Okay. Example 3 says a wave of speed 20 meters. When he said a wave of speed 20 meters on a string fixed at both ends, of course, this is not the speed of the resultant wave, the speed of the 2 interfering waves, okay? The 2 waves which are going to form the standing wave, okay? The speed is 20 meters per second because we said the standing wave actually is not traveling, it is standing, okay? That's why they call it standing wave, okay? Now, the standing waves is this here. This is the equation for the standing wave. That's y equal ym sine kx, 2ym sine kx cosine omega t. This is the equation for the resultant wave. That's omega is here, k is unknown, and this is 2ym, okay? That's 2 times the amplitude of each one of the 2 waves which are forming these standing waves here, okay? Where x and y are in meter and t is in seconds. Generally, we always use SI units. What is the distance between 2 consecutive nodes? You want the distance between 2 nodes, which means this, for example, this distance here. And I told you, and I'm sure you remember it, that the distance between 2 nodes is always lambda over 2. Always. Okay? For example, here I have lambda over 2. You see the length is lambda over 2. Here I have lambda over 2 and lambda over 2. I have lambda. So the whole length is lambda. So the distance between 2 nodes, let me write it down here. Clearly, the distance between 2 nodes is always, between 2 nodes is always, very important, always equal to lambda over 2. So if I can find lambda from this problem, then I can find the distance between 2 nodes, okay? Now, consecutive nodes, yeah, exactly. Distance between 2 consecutive nodes. Let me add here the word consecutive, consecutive nodes, okay? Consecutive nodes. All right? Nodes, okay? So I have the distance between two consecutive nodes here, okay? The distance between two consecutive nodes is always lambda over 2, okay? Now, lambda, of course, lambda is lambda, we know the equation, V equal lambda F, okay? So lambda is V over F. V is given 20 meters per second. He gave you omega, so you can find the frequency, right? So here, 20 meters, okay, per second, divided by the frequency, which is omega over 2 pi, 30 over 2 pi, okay? So you get this, you get the wavelength in this problem. The wavelength will be 4.2 meters, okay? That's the wavelength in this specific problem, okay? Now, if I divide this by 2 to get the distance between two nodes, so my distance between two nodes, this will be 4.2 over 2, which is 2.1 meter. That's the distance between two nodes, okay? All right? The next problem, or next example, example 4. By the way, these are problems from old exams. So you can see how difficult or how easy are the old exam problems. You decide by yourself, and of course you have to practice a lot. You don't only rely on this few problems that we solve in front of you here. You have to go by yourself and start solving old exams and start solving end of chapter problems. Very important to solve end of chapter problems. Example number 4. It says a 50 centimeter long string. So this is the length of the string. He gave you the length. And mass 0.01 kilogram is stretched with a tension of 18 Newton. He gave you the tension which is in the string itself, okay? And this is between two fixed supports, which means there will be standing waves in this case, okay? What is the resonant frequency of the longest wavelength on this string? Okay, my son, can you tell me what will be the longest, which shape here will give you the longest wavelength, which means the highest wavelength? Remember that the lambda here is 2L, and lambda here is L, and lambda here is what? 12 over 3, and so on. So as we move down, the wavelength is decreasing. So the longest wavelength will correspond to this case here. Okay? That's the longest. So next, let me write down. The longest wavelength, another, again, important concept is 2L. Lambda equal to L, okay? That's the longest wavelength. It's 2L from here. Lambda is 2L. That's the longest wavelength. And that's the lowest resonant frequency. This is also the lowest resonant frequency, okay? Because the frequency and the wavelength are inversely proportional. One of them increases, the other one decreases, okay? That's the lowest. So, the longest wavelength will be 2L. Okay? Now, but he wants the frequency. He doesn't want the longest wavelength. He wants the frequency. So we're talking about F1. Okay? So here we're talking about F1. The longest wavelength corresponds to the lowest frequency. Very important. Okay? So F1, which is V over 2L. Now L is given to you is 0.5 meter. Okay, we have to change the meter. V, we go back to the old idea of tension over mu, okay? Not the speed of the wave, okay? The tension is given to you is 18 Newton, and the mu you can get it from the mass per unit length, okay? So mu is m over L, which is 0.01 divided by the length, which is 0.5 here. And this will give you a mu of... the mu will be 0.02 kilogram, 0.02 kilogram per meter. Okay, so this is the mu. So V will be square root of what? A tension which is 18 Newton over 0.02, and we take the square root to get the speed of the wave, which is 30 meters per second. So the speed of this wave, of the two waves interfering, is 30 meters per second. So I know the speed of the wave, I know the length of the string, I can find the frequency, the resonant frequency. How did I know I have to use F1? Because it's telling you in the problem that it gives you the longest wavelength. Longest wavelength means the smallest frequency, okay? Or the lowest frequency. So it will be 30 divided by 100, which is 1 meter, okay? 1 meter, okay? Then it will be 30 hertz. That's F1 in this problem. How about, what is the second resonant frequency? It will be 60 hertz. 30 hertz, huh? 30. The second resonant frequency will be 60 hertz. The third resonant frequency will be 90 hertz, and so on. So every time you add, to go to the next higher frequency, you add F1, you add the 30 hertz. I hope these 4 examples illustrate the idea of the standing waves and give you an idea how to solve problems. Now, my son, you go and by yourself and try to solve problem by yourself. Don't rely on these videos or on the lecture or on the recitation. You have to go by yourself and start solving all the exams and start solving end of chapter problems. Thank you very much.